Section 4.2 will finish our discussion of historical numeration systems. We are going to continue with some of the same ideas as we move into 4.3 and 4.4, but they won't be from historical perspective. So our last two numeration systems that we're going to do today are Babylonian and Mayan. And they are a little more complicated than the Egyptians, the Romans, and the Chinese. The Egyptians, Romans, and Chinese had some funny symbols and things like that, but for the most part, there was a repetition process. We repeated things, and the Chinese, they weren't necessarily repeated, but they were multiplied by powers of 10, which is kind of like our system with these powers business. These two systems today have some nuances that are quite different from those. And they're more similar to one another than they are to the ones we did before. That's why they've put them together. So the first one we're going to look at is the Babylonian numeration system. The Babylonians actually only have two symbols. So that part's really friendly in the sense that there's not a lot of drawing. And their symbols are very easy to draw. So the first one for the value of 1 looks like what we would probably refer to as an upside down triangle, if triangles indeed had direction. When I draw them, in a moment here, you're going to see that I'm probably going to just leave them not filled in because there's, kind of a shorthandish to them. When you're doing them inside of my math lab, you're not drawing them anyway. You're going to be selecting from a multiple choice option, so it should be okay. And then the value for 10 looks kind of like an arrow pointing left or like a less than sign, and then it kind of fills in this way. And again, I will abbreviate it when I draw it, and it will really just look like an arrow pointing left or a less than symbol. So some features about their system. Their system does use repeated symbols, but only for values less than 60. So if you wanted the number, say, 42, you'd do 4 of the arrows to get 40, and you'd do 2 of the triangles to get 2, and that'd be 42, and you'd be done. So if the number is less than 60, it's just repeated symbols, a lot like the Egyptians. But if its number is bigger than 60, they have a positional process. So their positional number system is based on the number 60. So they have 1, and then we have 60, and then 60 squared, 60 cubed, and so on. Our system is based on the number 10. So we have 1, we have 10, and then we have 100, which is 10 squared, 1,000, which is 10 cubed. So we use powers of 10, they use powers of 60. Okay? I didn't mention it last time, so I'd kind of like to mention it now. Any idea why we have a base 10 number system? Yes, it's 10 fingers. That's why. So if God had make you like Fred Flintstone or like most of the cartoon characters on television, they actually only have they have thumbs, but they're missing like one of their fingers, and they look like this, right? They have like 3 fingers and a thumb on each hand. I don't know if you've ever noticed that about cartoon characters. And if that's how God really had made us, we probably would be using a base 8 number system, because that's why the base 10 came about, was our 10 fingers. So their base 60 number system for the Babylonians is a little bit different, but it actually works quite similarly to ours because of the powers of 60. They do lack a 0, and we'll see that come into play being a problem in the middle of one of our examples. But it won't be a problem from the standpoint of, oh my goodness, I got it wrong because there was missing a 0 and I didn't know that that's what they meant. It's not going to be like that. It's just a flaw in their system. So I want to point that out because I want you to be aware that there are reasons why these systems don't exist, and lacking a 0 is a pretty significant reason, and you'll see how it would come into play back in the day, if you will, and why it would have been a problem. So what we're going to do first is we're going to take a look at a couple of numbers in their system. So you see lots of arrows and triangles, right? So the first thing that we have to know is we have to know where place values change. So in their system, they always do the larger value, which is the arrow, in front of their smaller value, which is the triangle. So at this location, right here, on the left-hand side, you see arrows and then a triangle. And then you see it switch back, if you cross my yellow line, back into arrows. Well, when it switches back into arrows, it changes place value, because their arrows always come before their triangles in their place value. So what we're going to do when we identify these first is draw in where our place value changes occur. And we'll draw them in with lines, vertical lines. So in front of the yellow line, we have 2 arrows and we have a triangle. Using their system, what would that number be? 21. Each of the arrows is 10, and there's 2 of them, and the triangles is 1, and there's 1. So this is the number 21 before my yellow line. Okay? How about after the yellow line? 22. It's 22. Now, this is not the number 2122 or 2122. It's not. You can't just string them all together again. You have to take into consideration that they have base 60. So over here, this is the ones place. The ones place is always to the far right, just like our system. That's actually very friendly for us that it works that way. Smallest value on the right. And then their larger place values go towards the left. So if we were in our system, this would be the tens place. Well, in their system, it's the 60s place. So I'm just writing the numbers underneath them to represent what place value I'm in. And in a moment here on this next example, number 2, we'll have more than 2 place values, and you'll see how that plays out. So imagine that we're going to do it with money because you have a picture in your head of money pretty good. Okay, like bills, okay? So imagine we had $1 bills, which we have, so it's a good thing to imagine, right? And $60 bills. Okay, just $1 bills and $60 bills for this problem is enough. What this is saying is that we have 21 $60 bills. Is there a way that you could figure out how much money that is? What would you do? You'd multiply, right? So we have 21 $60 bills, and then we have 22 ones. We can imagine that pretty easily, 22 ones. So we're going to multiply. So when we get to the point of actually calculating this, we take our 21 and we multiply it by the place value 60. And then we take our 22, technically we multiply it by a place value of 1. It's not very exciting, but that's what we're doing. All right, so you're going to want your calculator today. So if you have a calculator, go ahead and grab that out. If you have your phone and that's all you got, I'll let you use it today. It's okay. It's really important when we get to this test that you're going to have a calculator with you. Not because I won't have one active and available inside of my math lab, because it'll just be a hassle to use it. You are going to do a lot of calculations in Chapter 4. Okay? So we need to do 21 times 60. So what is 21 times 60? You did it.
I did it.
Yeah, okay, so 1,260, right? And then we have our 22 at the end. And you're right, Tracy, I have 1,282. Is that all right? So we're going to try it again, but before we do, is that one all right? All right? Okay, so we're going to look at number 2. And we always start with deciding where the place values break apart. And they always break apart when we change from a smaller value, namely a 1, to a larger value, a 10, as we're moving from left to right. Okay, so bigger symbols in front of smaller. So these are okay, where I've got 4 of the arrows and then 3 of the triangles being together or grouped together. But after that, I have to break it apart. And then I have 2 arrows and a triangle, and then it goes back to an arrow. So it breaks apart here as well. You do have to group them in the right places or you're not going to get the right answers. So just on the last one, we're going to take each of the pieces separately that are sort of bracketed off by the yellow lines and figure out how much is there. So what do we have? What value do we have before the first yellow line? 43. Whoops. How about sort of sandwiched between the 2 yellow lines? 21. And then after the last yellow line? 11. Okay, is that good? Everybody knows where all those numbers came from? Excellent. And we're just going to put underneath them the place value. So it always starts with the 1's value on the right and moves backwards. So this is the 60s place. We have 3 values this time, so this one is actually 60 squared, and if we had 4 values, we'd have 60 to the 4th, and then we'd continue on from there. 60 squared is equivalent to 3,600. Okay, so far so good? Okay, so the analog to what I just did a moment ago is that now not only do you have a $1 bill and a $60 bill, you also have a $3,600 bill. This is very exciting news, right? It's a big bill. Okay, so you have 43 $3,600 bills. And you have 21 60s, and you have 11 ones. So every time we do this, we're multiplying the place value times what's in that place value. So the first place value, the 3,600, gets multiplied by the 43.
15,480.
Okay, I'll write that down. What'd you get, 15,000? Oh, I think it's bigger than that.
154,154,800. I had 1 0 off.
154,800? Okay, all right, we'll keep going. And then we have 21 60s, which we did that above, actually. So that one was 1260, I think, yeah? And then we have 11 ones. Okay, so we have 154,800 plus 1260 plus 11. What is my grand total?
156,071, I believe.
That's what I have too. Is that all right? Okay, so in my math lab, when you encounter a problem like this, it will look exactly like this. They're going to give you a Babylonian numeral, and they're going to say, find its Hindu Arabic. That's our number system's name. We have the Hindu Arabic number system. Find the Hindu Arabic equivalent, or something like that. That's what it's going to say. And it's going to have you write in, like the 156,071. It's going to make you type that in. Because you have the ability very easily to type in numbers into my math lab, right? Yeah, no problem. However, when we get to this problems over here, it's not going to look like that. Here, we're taking our number and we're turning it into a number that looks like the triangles and the arrows and things like that. And I'm sure that someday my math lab will probably advance enough that they will be able to have like drag and drop kind of stuff, you know, where you can move the symbols in. But they don't do that way yet. It's multiple choice. So one option you have, because it is multiple choice, is that they're going to give you maybe 4 or 5 answer choices, right? Let's say 4 for the sake of argument right now. You're going to choose between A, B, C, and D for the answer choice. So what you could do if you wanted is you could take answer choice A and do exactly what we did over here and turn it into the number and compare it to the number they gave you. And if it doesn't work, you go on to answer choice B and you compare it to the number they gave you. And whichever one finally hits on the number you gave you, that's the right answer choice. Does that make sense? It's not a terribly efficient thing to do, but it could be done. Agreed? And you would hate it if it's D. And you would hate it even more if you got through A through D and it was none of those, which means you actually made a mistake somewhere along the way and you have to do it all again. Right? Not terribly efficient, but you could do it that way. So instead, I'd like to show you how you could do it from a more efficient standpoint. So inside of problems 1 and 2, the basic operation that we used. Okay, we're back online. So what we worked with on problems 1 and 2, the basic operation we used was multiplication, right? We multiplied the place value times whatever was in its place value. So if it's the place value 3,600, we multiplied it by the 43 that was in that location. So since multiplication is how we turn their numbers into our numbers, what do you think we're going to do to turn our numbers into theirs? Division. So we're going to be working backwards. We're going to be using division. And it's important when we do this division to recognize what the place values in their system are. So we have the ones place, and we had the 60s place, and we had 60 squared. I'll write it underneath as 3,600. And we would have 60 cubed. Somebody tell me what 60 cubed is. That's 60 squared.
216,000.
216,000. Yeah, it's going to get real big real quick. 216,000. And we could keep going if we needed to, right? So what we want is we want to choose the biggest one of those values that divides into the number we're working with. So on part A, or 3, number 3, our number is 3,280. So I want to divide it by something smaller, but the biggest thing that's smaller. Like I don't want to divide it by 60 or by 1 maybe, right? I want to make sure that I'm dividing by whatever's the biggest thing smaller. So I don't want to divide it by 216,000. That's too big. I don't want to divide it by 3,600. That's also bigger than 3,280. So the next place value down would be 60. So this one will be divided by 60. Now, think old school, 3rd grade, 4th grade, long division. Okay, that's what we're doing, but we're not going to do an abbreviated version of it. You put the 3,280, under the bracketing or under the house, sometimes people call it, and you put the number 60 outside. Agreed? Okay, so I'm going to impose a little bit more structure on it so that we can actually process all of this together. We're going to put a line underneath the 60, and we're actually going to enclose the 3280 like that. So this is a division scaffolding. It keeps all of our work nice and neat together. It makes it easy to read when we're done. So it's just friendly. But it's just the division, the same division you've done all along. So what you're going to do, not from the long, division standpoint of 3rd grade where you did it without the calculator, you're going to use your calculator. And you're going to take your calculator and you're going to say, okay, 3280 divided by 60. And what we want to know is the whole number of times it goes in. I don't care about the decimal that shows up, just the whole number. So how many whole number times does 60 go into 3280? 54. And the next thing we're going to do is we're going to multiply the 54 by the 60 out in front. So what is 54 times 60?
3,280.
3240. Okay? And we subtract, just like with long division. So what is 3280 minus 3240? It's 40. And then we go down one place value. So we started with the place value of 60. The one before that happens to be the number 1, so we'll use the 1. How many times does 1 go into 40? 40 times. 40 times 1's 40, and we have 0. What's your question, Isabel?
Why is it 40 less than, why did we subtract 3240?
Because that's 54 times 60.
Because those don't equally divide up into 16.
Oh, because it's the decimals after.
Yes, exactly. They don't evenly go in because of the decimals after. You're right. And this is the point when you're done, when you get a 1, when you're dividing by 1, and you have a 0 remainder. Those two things together are what tell us that the problem is done in terms of the division. Okay, everybody good so far? Okay, do you have a question or no?
The number on the right, what we make the symbols out of?
Yes, the numbers on the right are what we're going to make our symbols out of. So that 54 and that 40 are exactly the same as what the 21 and the 22 were over here. They're how we're going to make our symbols. So we think about 54 in terms of the 10s and the 1s. And what does it tell me that I need?
5
5
tens.
10s, which is 5 arrows. I'm going to write it a couple of different ways so you can see how it could be written. 5 arrows and 4 triangles. So depending on who would have been doing this at the time, they might write it all out long ways like this. Or you might see it kind of like on the second example here where they've stacked some things. They tend to do the stacking either evenly, if it splits evenly, or 1 extra on top. So it might instead look like this, 50, like that, and then 4. And notice, remember I told you I was going to shorthand writing these out, not filling everything in, but it might look like either of those, okay? So let me move this one down just so I'm not confusing the issue. Then I need the number 40. So how do I get the number 40?
4 left.
4 arrows. So if I'm writing it again a long ways, then this whole thing is my answer. Okay? Or if I'm writing it stacked, it might look like that. And it's not like somebody's going to trip you up and make one of these answers B and the other one C or something like that. That's not what's going to happen. It'll just show up in one of the versions. Stacked tends to be more common. Okay, so we have 54 followed by the 40. All good? Okay, so we're going to do the same process on number 4, 43,205. But we have to again reconsider, what do I divide by? Don't just automatically assume, I'm just going to divide by 60 every time, because you're not. This one will divide by something that's a place value bigger than 60. What will it divide by? 3,600. So we need to start by dividing this one by 3,600 on the outer left side with the 43,205 underneath. Okay, and our calculator's our friend. Going to do that division for us. So we want to take 43,205 and divide by 3,600, and we only want the whole number part. 12. Awesome. Is it 12?
Mm-hmm.
Great. Okay. And we take that number 12 on the right and multiply it by the 3,600 on the left to find out what we subtract. And what do we subtract?
43,200.
Ooh, almost all of it. Now, for the purposes of this particular example, well, we have a remainder of 5. We could just jump down to dividing by 1 and we could be done. But in general, that's not what we want to do with what I know is coming up soon. So we're going to divide by every place value, even if it doesn't go in. So the next place value down is the 60s, and I'm fully aware it doesn't go in, so it will go in 0 times. And we will subtract the 0, and we will feel funny doing it, but it will be okay. Okay? So there's 0 60s in the number 5. And then our last place value is the place value of 1, which goes in 5 times, resulting in my remainder of 0. Okay, so these numbers over here, 1205, tell us what we are going to draw out. How do I draw the number 12?
One arrow and 2 triangles.
1 arrow, 2 triangles. How do I draw the number 0? You can't. And that's a problem. Let's move on. How do I draw the number 5?
5 triangles.
5 triangles.
We put them next to each other, don't we?
So here's the catch. The 5 triangles I just drew, and they might be stacked, right?
Looks like 17.
If they all run together and there's not a discernible left space, it looks like 17, doesn't it?
Yeah.
Now you could fix a little bit if you stack things, maybe, right? But you still can't fix the 0 issue, right? It very much, at the very least, looks like this is 5 in the 1's place, and maybe this is 12 in the 60's place, not 12 in the 60 squared's place. And you can imagine, bookkeeping purposes wise, this wouldn't be good. Because if somebody owed you $43,205 and you, through a bookkeeping process, made the number look an awful lot like 17, that's not good, right? So there's not going to be any problems that show up that mean, oh my goodness, I got the answer wrong because there wasn't a 0 and I didn't know how to write. That's not going to happen. That's not why I mention it. I mention it because these historical systems have flaws. There's a reason they don't exist, right? There's a reason that the Hindu-Arabic system is the universal system for mathematics worldwide. No matter what language you speak or what culture you're from, that's what we use. So this is one of the flaws. Any questions on that? Yeah, Isabel?
Is there a reason you couldn't go straight from 360, like when 5 is left on the second one? Why couldn't you just use the 1 there?
Yeah, so in the Babylonian system, no, there's no reason you couldn't. I mean, you really could and it wouldn't hurt anything. But you're very quickly going to see another system where it needs to be there. So by default, if we just always put it there, we don't have to remember, is this the system that I needed or is this the system that I don't? So I would encourage you to always put it. And also when we get into section 4.3, it's going to become another issue where we're going to need it again too. Yep,
In my
Benjamin.
math lab, do we just put all of them together? And
So
just-
in my math lab, what they're going to do is they're going to give you multiple choice answers.
Okay.
So on this one, you probably would see a little bit of a space between it or something like that. But you still don't have a way to designate that there's a 0 lying between them either. So yeah, it's multiple choice. Okay, we have another system. Our other system we're looking at today is the Mayan system.
So 0
It does have a 0. It has other problems, but it does have a 0.
They were, if I remember correctly, they were one of the few civilizations independently developed.
Yes, they were. Yeah, the Mayans were one of the earliest civilizations to have a 0. In fact, they're the only civilization that we've seen a historical numeration system of that has one. The Romans didn't. Who else do we have? The Egyptians didn't. Obviously, we just did the Babylonians, and they didn't. And then the Chinese did. So that was one that did as well. Which is drawn crazy. You're right. Yeah, back in section 4.1. If you've seen that video, yeah, it's crazy. Yep. Jonah.
Because they were, most other cultures were using it to count money?
It could be. I don't know. I don't know necessarily the why. The Mayans definitely had a lot of advances that other civilizations didn't. We're actually going to talk about their place value system too, which is a little bit unique. But let me do their symbols first. You may not like the symbol for 0, but it's not as bad as the one that we had for the Chinese. So it looks a little bit like a football or like a shell, like a clam shell. That's not the best drawing ever. But it looks something like this. You'll know it when you see it because it's the only thing that looks like this. Their symbol for the number 1 is a dot. And their symbol for the number 5 is a horizontal line. It's very short. Okay, their system is written vertically, like the Chinese did, okay? Where they put the biggest place value on top, the lowest place value on bottom. And we should all be very grateful that all of the systems did those sorts of things in common, right? Biggest on top, smallest on bottom, biggest on left, smallest on right. Those are really good things for us to be able to think about their systems because it's similar. They do have dots that are written on top of the lines. So in much the same way over here where they always did the arrows in front of the triangles, right? In the Chinese or in the Mayans, they always do dots on top of lines. They do a modified base 20 system. So let me just talk about what the base 20 system would mean first. We have a base 10 system, and Ben told us that the reason for that is because we have 10 fingers. Any guesses as to why the Mayans might have used 20?
Because of fingers.
Fingers and toes, absolutely. Because, I mean, as much as maybe everybody in the room today is wearing something closed-toed, that's not what it looked like in the Mayans' time, right? Right? Sandals, maybe, barefoot most of the time, right? So that's the 20 where it's coming from. Their system is not just a base 20 system, though, right? We have 1, and then we have 10, and we have 10 squared and 10 cubed. They have this funny thing where it's a modified base 20 system. So they have 1, and they have 20, and then they have 20 times 18, not 20 squared. And then after the 20 times 18, then they start putting powers on the 20s. So 20 times 18, and then 20 squared times 18, and then 20 cubed times 18, and so forth.
Why times 18?
So somebody grab a calculator and tell me what is 20 times 18? 360. Any idea why 360 might have been important in the Mayan culture?
Whole year.
Yeah, that's their approximation for a year. So they believe they're a very calendaring system. You guys might remember that they predicted the end of the world in 2012. We're still here 10 years later, but they did. 2012 was going to be the end of the world. Calendars were really important. So their estimation for the length of a year was 360, and it was a valuable enough thing that they wanted it to show up in their number system.
They had 18 20-day months.
So there you go.
So
All right, so we've got the 360, and then we start doing powers of 20 after that. Okay, the 18 is still in there, but it's powers of 20 after the 20 times 18. And then they repeat the symbols within the position just like the Babylonians. So if they had a number that was like 15, they'd do 3 bars, because that's 3 5s, right? If they had the number 7, they'd do a bar and 2 dots. So repeat the dots, to get the extra values within the systems. So we're going to do the same thing we did for the Mayans, or for the Babylonians. We're going to do that for the Mayans. We're going to take Mayan numbers, and we're going to turn them into our numbers. That's our first place. So we see dots and bars, and over there on the right-hand side on number 6, you see one of those shell things, the zeros. So again, just like with the Babylonians, we need to make sure that we understand where the place values change, because you can't just put random bars in there and call them all different place values. That's just not how they would have done that. So one of our features over there said, previous slide, that dots went above bars. So the 4 dots on top with the bar underneath it could be grouped together, right? Reasonably so, yeah? So this is the location for our first place value change, because after I did the dots and the bars, I have dots showing up again underneath. So I have to change place values. And that's it, actually, on this one, because then I just have dots and bars more, and there's no more dots that show up, so I'm done in terms of changing place values. Looking at the dots and the bars above my yellow line, what number is represented by a bar and 4 dots?
7.
Nope,
9.
9. So we would have 5 plus 4. The line's 5, and the dots are each 1, so that's 9. How about below? I have 2 lines and 4 dots.
14.
That's 14. Okay, we're going to do the same thing that we did with the Babylonians. Too many people. We're going to write them out. We have the ones place, we have the 20s place. We have 20 times 18, which we already said was 360. We're going to write out a couple more. Now we have 20 squared times 18. So what is 20 squared times 18? 7,200. And we'll do just one more, but we could keep doing this indefinitely, right? 20 cubed times 18.
144,000.
All right, so we could go on like this indefinitely.
Those numbers work out a little bit nicer than the Babylonians.
They do. That times 18 in there gives us some very nice numbers, actually. Okay, so the lowest value, that's my 14 right there, is the ones place, and we work our way up from there. So this is the ones place, and this one's the 20s place. This one actually works much better, this example anyway, for our money, because we really have $20 bills, right, that we do. So if you had 9 $20 bills, just like before, we would be multiplying. You could figure out very easily how much money you have, right? 9 times your 20. And you have 14 ones. So what's 9 times 20? 180. And then 14 times 1 is 14. And if we added those together, we'd get 194. Okay. So where do you think I'm going to draw my bars to break things apart for my number 6?
Between the last line on the top and 0 indicator.
Okay, so this is one of those places, you bet. That 0 indicator is definitely a place value change. And everything above it can all be grouped together, right? Yeah. Where else? Okay, we would also have one here right above that dot, because we went from a line to a dot.
Between the 0 and the line.
Yep, and we would have one between the 0 and the line. So it's really tight in here on this one. But yeah, those are the places. So we have 4 place values because we've separated it 3 times. What is the value above the first yellow line?
17.
17. And then we've got our 0, right? What's after the 0?
5.
That's 5. And on the bottom?
6.
6. Is everybody good with that? All right. So we start at the bottom. This is the ones place, and then the 20s place. And then we have the 360. And then what do we have?
72.
The 7,200. Okay, so we're going to multiply each of those and then add them together. So I'll write mine out just to be sure that you see it clearly. We have 17 times the 7,200. Technically, we have 0 times the 360. I realize that's 0. You don't have to write it if you don't wish. We have the 5 times our 20. And we have our 6 times our 1. All right, what is 17 times 7,200?
Is it 122,400?
It is. Good job. The next one's a 0. Then I need 5 times 20, which is 100. And then I have my 6 on the end. So 122,400 plus 0 plus 100 plus 6 gives me,
122,506.
yes, it does. Okay, so again, if that multiplication process and breaking things apart is something that you like to do and you want a multiple choice answer to do that and do it several times within a problem, you can keep doing that. But if you want to do something more efficient, we're going to do a division algorithm to go the other direction, just like we did before. As a reminder to us, I'm going to move these at the top to the other screen. These are our place values that we're going to be dividing by. So we want the biggest place value that goes into each individual number. So 208, what is the biggest place value that's going to go into 208?
20.
Yeah, it's just 20. So not a very big one. I have 20 dividing into my 208. How many times will 20 go into 208? 10. And 10 times 20 is 200, leaving me with a remainder of 8. Okay, going down in place value, the place value before the 20's place is the 1's place. And how many times will 1 go into 8? 8. And multiply and subtract to get a remainder of 0. Now, just like with the Babylonians, the 10 and the 8 tell us what to draw. How do I draw a 10 in Mayan?
2 lines.
2 lines. And how do I draw an 8 in Mayan?
3 dots.
1 line and 3 dots.
Yep, 1 line and 3 dots, or 3 dots and 1 line. Yep, as long as the dots are going on top of the line, right? This is the number 208 in Mayan. Okay, ready to do one a little bit bigger? 58,532. I'm going to shift this over just a little. So what is the first value I will divide my 58,532 by? 7,200 is it, yes. So if I divide it by 7,200, how many times will 7,200 go into 58,532? 8. And then I need to multiply 8 times 7,200 to give me
57,600.
wonderful. Now we're going to subtract. What do we get if I subtract? Yes, 932. Okay, and we'll go down 1 in place value. So I'll spoil the fun real quick to just tell you that we're going to need all the place values. But even if the next one, it's 360, didn't actually go into the 932, we'd still want to represent it. Because if it goes in 0 times, we will actually have a 0 we can draw now, right? That's why we need the 0 present on this particular number system, whereas in the last one, we could have sort of avoided it if we didn't want to mess with it. This one does go in, though, right? 360 does go in to our 932. How many times? Twice. We multiply that to get 720. What is 932 minus 720?
212.
212. Place value down from 360 is 20. Before we get to the 1, we got to do the 20.
10 times.
And it will go in 10 times. That's 200. So my remainder is 12. 1 will go into 12 times, giving me a remainder of 0. Okay, everybody good so far? Okay, so these numbers over here on the right are what I'm going to draw. An 8, a 2, a 10, and a 12. So how do I draw an 8?
3 dots in a line.
3 dots and a line. How do I draw a 2?
2 dots.
How do I draw a 10?
2 lines.
And how do I draw a 12?
2 dots and 2 lines.
Okay, so let's first just establish the fact that you've done everything correct and this is the correct answer. However, do you see a problem with the system? What's the problem that you see, Jacob?
In the middle, the 2 dots and 2 lines.
Yeah, so when I had the two dots in their own place value, and then I had the two lines in their own place value, this looks just like 12, doesn't it? Yeah, that's a problem, and there's not any way to fix it. You might say, well, could you just leave a little space there? And you could, but it's kind of like with handwriting, right? Like, how much space is enough to know for sure? What if it looks like there's enough space, but maybe that person really just was spreading their work out when they wrote their number down? It's a little bit fuzzy, right? It is, and that's a problem. Again, it's not a problem for us. We recognize it, but that's the reason, I mean, among others, I'm sure too, that this system has not withstood the test of time, right? There's a flaw in the system that makes it not workable. It doesn't work very well anyway. Any questions? Okay, so pause just a second while I tell you what's going on. Sections 4.1 and 4.2 are inside of one unit. I think that makes it unit 5. No, that's not right. Maybe it is unit 5. Whatever it is called, it's unit whatever, okay? 4.1 and 4.2 are grouped together, okay? They're not due till Thursday. We are going to do new material 4.3 on Wednesday. It just won't be due on Thursday. So you've got about 3 days to get done this homework and this quiz for sections 4.1 and 4.2, and they're all complete now, okay?